Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X published on January 5th, 2026, just 2 days ago. It introduces a new benchmark suite that achieves a 13 times speed up on average, tackling the critical issue where nearly 20% of model development compute is currently wasted on inefficient evaluation. The paper is titled DatBench, Discriminative, Faithful, and Efficient VLM Evaluations. And as we'll see later, the findings on how much standard benchmarks inflate model capabilities are quite eye-opening. Well, Figure 1 breaks down exactly how they maintain quality while cutting costs. On the left, Panel A plots discriminative power against the fraction of data used. You can see the solid blue lines rise steeply and level off, meaning they capture nearly all the signal using only about 40% of the samples, whereas random selection, shown by the dashed gray line, lags far behind. Then, shifting to Panel B on the right, the bar chart translates this into raw time savings. It compares H100 hours for original benchmarks against DatBench, revealing massive efficiency gains, specifically a 49 times speed up for general capabilities and 24 times for document tasks. So having seen the efficiency gains in the previous figure, Table 1 now itemizes the 33 datasets that make up the full evaluation suite. The authors categorize these into 9 capability pillars, ranging from chart understanding at the top to general visual question answering at the bottom. Notice how the document and scene optical character recognition sections combine standard baselines, like text versus QA, with tougher, in-the-wild challenges. This ensures the benchmark covers everything from parsing receipts to solving complex geometry problems in the math and logic category. Alright, to visualize how these tasks fit together, Figure 2 displays the 9 capability pillars used for evaluation. The top row emphasizes extracting information and applying logic, spanning chart and document understanding, scene OCR, math and logic, and spatial reasoning. Below that, the second row targets perceptual grounding and general knowledge, with categories like counting, diagrams and tables, and general VQA. By partitioning tasks this way, the authors can distinctively measure whether a model struggles with low-level perception or high-level reasoning. Well, Figure 3 reveals just how much standard multiple-choice formats inflate perceived model capabilities. In Panel A on the left, we see a comparison between standard multiple-choice accuracy on the horizontal axis and generative accuracy on the vertical axis. The fact that every point sits significantly below the diagonal line indicates that models often guess correctly from a list, but fail when forced to generate the answer themselves. Shifting to Panel B on the right, the authors apply circular evaluation, which rotates the answer choices to ensure consistency. Once again, accuracy on datasets like Bench and real-world QA drops sharply compared to the vanilla baseline, proving that simple guessing strategies were artificially boosting scores. Moving on to Figure 5, the authors quantify the impact of their quality filtering pipeline across different skills. The chart plots the percentage of discarded samples on a logarithmic scale, breaking down reasons like incorrect ground truth, ambiguity, and low resolution. Look at the spatial capability on the far left. It suffers a massive drop, with over 40% of samples removed due to severe noise. Conversely, the grounding and general categories on the right appear much cleaner, requiring almost no filtering because their underlying data is already well curated. So, Figure 8 brings all of those filtering steps together to show the final impact on model rankings. Here, the x-axis represents accuracy on the original benchmarks, while the y-axis tracks performance on the cleaned DatBench suite. In the general plot at the bottom right, points sit well below the diagonal, confirming that removing blindly solvable questions makes the test significantly harder. Conversely, looking at the counting plot in the center, scores actually shift upward because the authors removed incorrect labels that were unfairly penalizing valid answers. Finally, for document understanding in the top middle, the steeper slope indicates that the new benchmark better distinguishes between strong and weak models. Table 3 now lists the comprehensive results across all models, comparing the cleaned DatBench metrics labeled DB against the original scores. Scanning the general column on the far right, you can see that scores in the DB subcolumn are consistently lower than the original ones, reflecting the removal of those blindly solvable questions. However, the thinking models section at the bottom reveals a critical trade-off. While adding inference time reasoning boosts high-level tasks like math, it devastates low-level perception. For instance, notice how OCR accuracy for the QN3 thinking model collapses from 54% down to just 26%. Wrapping up, 2 major takeaways stand out. Quantity does not equal quality in evaluation. By rigorously filtering out noisy or blindly solvable samples, the authors achieved a 13-fold speedup while actually improving the benchmark's ability to distinguish between models. This suggests the field must pivot from raw score chasing to clearer, more faithful assessments. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.